to themselves in different ways. Okay, so gradient with no dot and no x maps a one-dimensional vector field to a three-dimensional vector field. Okay, and what that means is if you had the temperature everywhere, the gradient of temperature is where will the temperature move? It moves from hotter to colder. Okay, so gradient maps a one-dimensional vector field to a three-dimensional vector field. I have that written over there. Okay, then curl maps a 3D vector field to a 3D vector field. Okay, suppose you have the direction water is flowing at every point. The curl of that vector field will be another vector field pointing normal to it. If I have water that's going all like this point, then the curl will be the center of that circular flow. Okay, the curl takes one flow, produces another flow, the normal tangent to where your flow is. And then finally, divergence maps 3 to 1. Okay, so if I have a vector field already, like flow of water everywhere, divergence tells you it's like the opposite of gradient. Okay, so if I take the divergence of the gradient, I get that is a function which maps from 1 to 3 and 3 to 1. So we take the temperature and then say where's temperature flowing, and then say add up the definitions. I'm sorry, I should have a mouth. And then add up the derivatives of all the components. So in components, gradient is this. Okay, it is the derivative of so here we're using a different subscript. Eraser does not work very well. Gradient is the x derivative of a function f, the y derivative of a function f, and then the z derivative of a function f. And in that way, it maps a single function to a 3D function, to a vector field. Okay, the definition of divergence is you take, remember, it's a 3D vector field to a one-dimensional field. You just take the derivative of each component and then add them up. Okay, so if I have three functions, x, y, and z, then you just do derivative with respect to x of the function x, derivative plus derivative with respect to y of function y plus the derivative of z with respect to y. So that is divergence. It's the way to calculate it. And then curl is a nice little symmetric form. Hard to realize just looking at the numbers why curl does what it does, but the way you can memorize it is by recognizing that the x component involves derivatives in the y and z, the ones that aren't x. The y component involves derivatives that aren't y. The z component involves derivatives that aren't z. Okay. So again, the first component will be derivative in y, derivative in z. Next component will be derivative in x and y. Sorry, z and x, the ones not involving y. And last component will be the ones not involving z, i.e. y and x. And I'm not correctly, it should be x and y. And then the derivatives are sort of, you subtract them, and then you take the derivative with respect to of the other one. So that was yz, this is zy, this is zx, xz, this is xy, that's y. So that's how you can memorize formulas. If you knew how to take derivatives of single variable functions, you can now take derivatives of multivariable. I've now defined everything that is in these equations. I'm not going to do too much. Okay, at the end we'll do some more math, but we're going to go more conceptual here. So excuse me for digging through all. Are we good on? I have given some symbols and I've sort of defined what symbols are. Yeah.
What's the curl with the dot next to it?
That's divergence. It maps a 3D vector field.
What's the dot mean?
Just think of this as one symbol.
Oh, okay.
It's one symbol. It's one symbol. We're not multiplying. We're not taking dot product or anything. Just notation. Some people write it too. Anyway, so these are Maxwell's equations. You can expand it all out. Okay, if you don't want to do any vector calculus, you can stick to single variable calculus and just have 6 unknowns in your equation. That's fine too. This does have a solution. System of equations, meaning there is a choice of E, which has this property being true. And that choice of E and B, there's a lot of them. One of them is the canonical one, if you want to choose, is a beam of light pointing in one direction. Okay, so these can be solved, and you can actually get useful results from them. But I'm not going to do that yet. Okay. because these have some physical meaning. So when you take a derivative with respect to a variable, the unit of what you're taking a derivative of is divided by that. So what's the derivative of position with respect to time? Velocity. Unit of position is meters. Unit of velocity is meters per second. Dividing by time. Okay. So I write it. What's the derivative of velocity? Acceleration. What's the unit of acceleration?
Jerk.
Meters per second squared. So we went from meters per second to meters per second squared. Okay, divided by second. The derivative is divided by the unit that you're taking the derivative with respect to. Okay, so divergence, curl, and grad are 3D derivatives. They divide by meters, and derivative in time divides by seconds. Knowing that, let's play. Okay, so can we play before doing this? We'll get back to the units in a moment. See, my apologies, I'm slightly out of order here. Okay, what was your name, sir? Michael. Thank you, Michael. Okay, these are wrong. These are not Maxwell equations. This changes and this changes. Okay, so those are just the easy to remember version. It's in a vacuum if rho equals 0. That was 0. Rho is the amount of charge. It's a single variable. It's not a vector field. And where you have a point of an electron or something, that would be positive charge, negative charge. Where you have a proton, that will be positive charge. The field to the entire universe that describes the charge at every point. That's rho. Okay. So the real equation is that the divergence of E equals rho. And there's a quantity that gets added to this derivative in time, the electric field, that is the current, J. J and rho are related. Okay. J is amps. J is how much electricity is flowing. Current density. Thank you, thank you, thank you. So given that it's the current density, the technical equation is not that it's the derivative of rho with respect to time, i.e. how electricity is moving. The divergence of J is the change in electric field. Just another equation you have to know. People skip over this. People just say, oh, that's Maxwell equations. They don't mention that. Okay. All these stupid symbols are related. You need to memorize them. You don't have to memorize them, but you have to know that there's definitions. Let's get back to unit. Okay, so current density. Okay, I have it wrong in the slide here. We've got these terms for this stuff. The unit of unit of charge density is coulombs. Everybody here has heard of Coulomb? No? Famous guy. It's just the amount of electrical charge. So when you get shocked because you charged up your hair, you have 100 coulombs of charge in your head.
That's Avogadro's number.
I don't think so. I think so. Maybe if every molecule had a charge to it, and I think chemists may know the electronegativity of a molecule, then you could probably calculate the amount of charge in a given fluid, charged fluid. Acids are negatively charged ions. So if you have this amount of mole of acid molecule, you probably calculate the charge of a given unit volume of acid. There's a battery design. Anyway, okay, so rho is Coulomb. Yeah. Thank you. Okay, my slides are wrong. Given that rho is Coulomb, we know here that derivative of rho in time is Coulomb per meter squared, meter cubed seconds. And then because taking divergence divides by meters, we know that the unit of J, current density, is multiplied by meters. If you take a derivative of that with respect to position, i.e. divergence, then you get the correct units. And so that's it.
I'm sorry, what's the S?
Second.
Oh, second.
Meter per second, coulombs per second, coulombs per meter cubed. Okay, we can go further. So it's a little bit misleading because these still aren't Maxwell's equations. This one is a lie. This one is a lie because there's some factors that I missed. The units don't work here. Okay, there's actually a little thing that converts units here, and I'm not gonna talk about it. But the point is, if you might be misled if you just now you wouldn't do this. Okay, it's I forget what this quantity is, but it's like the it's called mu and epsilon, and it's the electronegativity of free space, or the electric permeability of free space.
That's what that's called?
Yeah. What? There's
Permittivity, permeability?
Permittivity?
No, I'm sorry, I'm not trying to be, I'm just saying, were you joking that you forgot?
I seriously don't know. I'm not focusing on it.
Okay.
Yeah, but I don't study this.
It's just like, no.
Anyway, so point is, you're misled if you use this, but sorry. Let's try and work out the units of the other quantities, right? I didn't do that here, actually. I assumed that the units of the electric field were newtons per coulomb. Okay, and the reason that is because electric field pushes charges. Okay, so it's like accelerating charges. If you have this much charge, you'll be pushed this much. Newton is the unit of force. Okay, so just like gravity will accelerate you, it's newtons. You know, the higher you are, the weaker gravity is. That's newtons per meter. Higher you are, more meters up equals less newtons being pulled to the right. So that by that assumption, E is newtons per meter. You have to remember Newton is kilogram meters per second squared, acceleration of mass. And you have to
Volts per meter.
second.
E is volts per meter.
Energy. Potential energy.
You may be right. You may be right, but let me continue the magnetic field.
Sure. Are you doing this at MKS?
No.
You're doing this at CGS? Yeah, what units are you using?
Whatever units are newtons and meters and seconds.
Another way to say it is, are you using SI units or Gaussian? Electromagnetics is discussed in several units, depending on whether it's the physics community
Yeah.
or the electrical engineering community. Which, by leaving the constants out, you can't follow which community you're using. Sometimes it's called Gaussian unit, sometimes it's called SI, which is the French word. What we often call MKS meters, kilogram second. So, do you know which units you're doing it in?
Yes, but I don't know the name of it. Okay, so I don't know what. This is not actually a coulomb. Okay, this is an atom's coulomb. Okay, and because every unit has a coulomb in it, that's my undetermined quantity, and I'm setting it that mu equals epsilon equals, which may be Gaussian. I'm not sure. Okay, so this book will probably say when mu
Is
equals.
that Griffiths?
This is yeah. This is, well, we can swap books. Did I?
Cambridge University.
Okay. I don't.
Okay.
Might occur here. Anyway, so I don't know what unit system I'm in. This is very astute. Okay, people do like to quibble over which units they're in and this and that. And I may have a glaring error here, and I hope I don't. But let me proceed to the magnetic field. So newtons per meter, E equals to newtons per E is newton per coulomb. Okay. Maybe spreading a lie here, but let's proceed to the magnetic field. That's force on charges. Yeah. Okay. So we can calculate the unit of B from this other stuff, right? So let's just naively take this and say the curl of E will give the unit of newtons per coulomb meter. Okay, and then that's the unit of the derivative of the magnetic field, which means that multiplying by time gives us the unit of the magnetic field as well. Newton seconds per coulomb meter. Does this make sense? Okay, so let me rearrange this slightly. We have to remember two things. We have to remember that Newton meters is joules, where this is not current. This is current density. This is a unit of energy, power. And we have to remember that amps is coulombs per second. Okay, so coulombs per second here is a reciprocal. It's seconds per coulomb. This is newtons per amp meter. And if I multiply and divide by meters, then we get joules per amp meter squared. The reason that's cool is because meter squared is area. Okay, and area. Yeah. So area is something people talk about with the magnetic field for capacitors, where if you have a given sheet in space, the amount of current flowing through that sheet, the more there is, the higher the amount of energy you store in the magnetic field through that sheet. So again, I may be spreading a lie here, but the relation between them is correct, where you can multiply and divide by meters per second velocity, as I said here, and derive that the units of E are essentially energy stored in the magnetic field. Okay. So the electric field is how how much force there is on charge. The magnetic field is how much energy is stored in a given area for amperage flowing through that. Okay. So those are the units of what we're actually talking about. The last unit I'm going to dwell on is voltage. So volts is the integral of the electric field over a particular path. So we have circuit, path is L, is the integral of the electric field strength along the path. You've got the definition of voltage. Okay, so I'll write that here, and then units are right there. Please check me on this. So is it correct that the unit of volt is joules per coulomb? No, Jeff? And the reason it would be joules per coulomb is because
Yes.
you need to go volt. Perfect. Okay. So voltage is the electromagnetic field integral with respect to position. I said derivatives divide by units, integrals multiply. So it's newton per coulomb times meter per coulomb, which is joules per coulomb. Now this is epic because this immediately tells us that voltage is energy per charge, i.e., higher voltage pushing through a wire means each charge packs more punch. Same electron, you get more energy in your system. So those are the units of the terms that occur in Maxwell equations and the definition of voltage. Okay, I want to introduce more. So I told you something interesting about the interpretation of the magnetic field earlier. Okay, to literally manifest that, all you do is take a double integral, an integral over a surface. Okay, so here's my region. Here's my region. Suppose I have a capacitor. A capacitor is a piece of metal that's wound up like this. Okay, and I can do it an integral over both sides here, over the entire surface of the magnetic field, which is pointing in all kinds of different directions here. If I perform that calculation, which if it was axis oriented would be really easy, it would just be integral from 0 to 1 of integral from 0 to 1 of dx dy of etc. Okay, if I do that, then we call that magnetic flux as simplify. And again, okay, somebody do the units here. What happens when you multiply the unit of magnetic field here by meters squared? What unit do we get out? Taking joules per amp meter squared and multiplying by particular. It's just per amp. That's joules per amp. Okay, so that's the unit of magnetic flux. Every single thing you possibly consider, radiation, any other quantities relating to amperage or voltage or current are derived from all these things. So this is magnetic flux. As we talked about before, in joules per coulomb, this is energy stored via, or the energy manifested via electricity flowing through a surface. I want to speak about this.
Excuse me, I
Yes.
guess this is not applicable like to gravity waves.
No. So the math is similar. But the units are different. I haven't spoken about how the version of equations with this being 0 and that being 0 manifests in waves. But it does. And you can calculate that the frequency of waves that would result. Anyway, so I wanted to do one more thing with magnetic flux here. We're going to derive the electromotive force. Okay, so we have to use I'm not sure how interesting this really is, but basically we have Maxwell's equations, and from the assumptions we can derive other facts. Okay, so I'm going to do a double integral over. Yeah, we'll start from this equation. Okay, so there's some situations where you are and aren't allowed to exchange various operators, derivatives, and integrals. And typically, you can just sort of do it and hope for the best. Although there are technical reasons for when you can and can't. Most of those technical reasons for when you can and can't swap derivatives and integrals relate to strange properties of functions. But if everything's continuous and nice, and there's no jumps or discontinuities in your functions, you can usually just do it. When you talk about physical systems, you kind of just exchange with no thought. So we're going to do that. This equation, do a double integral over some surface of minus dTB dA. We're going to exchange the derivative in time, take it out, assuming that it will work. This is the definition of phi. Okay, b dot the integral over the electric field over some surface. So that is the derivative in time of phi. And finally, we have to do some magic on the left side. So that's what I've just spelled out here. You interchange those operators. Okay, a double integral can be transformed into a line integral. Okay, so there's a theorem that says an integral over a surface over this piece of paper can be transformed into an integral over just the path surrounding it. If you take a derivative of the function you were integrating over. So we are, sorry, if you take an integral of the function if you take an integral of the function you're going over. So right now we're going over this guy. And instead of this guy, we're going to have its integral, i.e. we're going to get rid of the curl. Okay. The reason you have to do that is because this is a double integral over a surface. We're transforming to a single integral. Where did the second integral go? It was absorbed by this. Point is, we transform this. So up one by taking an integral of that guy, no more curl. And now down one, move an integral and add an integral, essentially. Doesn't exactly work like that. Completely focus way. I said it was magic. So the line integral, the loop around any particular surface, the electric field dot dl equals the change in time of the electromotive force. Okay, that's called Stokes' theorem. Okay.
So the first integration makes the curl go away.
Yes. So you can't just like get rid of an integral. These are fundamentally different. This is not a single integral. It's a path integral, it's a loop. When you're going over an area, you can convert an integral over this whole area to an integral just around the loop.
Okay.
Here. Yeah. Stokes' theorem. Green's theorem is another name for basic point.
So could that be viewed in terms of just, if you took that wiggly line and stretched it out, you could view it as a single dimension?
Yes.
Yeah.
And so when you actually do these computations manually, things get a little bit simpler. What you do, what you do is you take L and you say L is a line, some curve, some loop going. You just parameterize it. L is a function of t equals Lx of t, Ly of t, Lz of t. Yeah, go ahead. The integral of the normal vector would be this one. But the function you're integrating over essentially weights that. Okay. And so basically, if I'm doing it around this piece of paper.
Could you repeat the question for those online?
Oh yeah, thank you. I'm not even near the microphone.
You can pick it up.
Yeah, the question was if you do an integral, a line integral over a loop, is that like getting the area or the perimeter around that loop? And the answer is yes, if you have a very specific function, which is the normal where it's pointing. If you have a unit vector, which just points the same length for whatever point you're at, then you do calculate the length around it. But consider if this piece of paper was situated in, again, like the ocean, and it was being pulled this way and that way, then all along here, my function would be pointing that. And all along here, my function would be pointing that. And so I would get a net force of 0. Of course, the perimeter of the paper isn't 0, but the result of the integral is, because the net force is just pulling equally on both sides. Right. And the magic, again, is that the rules, Maxwell's equations are talking about the whole area, but it literally is decomposable to just around the perimeter. I am absolutely not doing this justice. You need to read more, you need to practice a lot more to get this, but the situation I just described can be literally done. If you just say integral from 0 to 1 of that function, you can break these up into simpler integrals. Okay, I'm not going to do that for you guys here, but all of this is reducible to high school calculus. My point of doing all this was to show the derivation of this rule. Okay, so this is actually induction. it says that a changing voltage. Sorry, this is the definition of electromotive force. This left part, the contour integral of the electric field over V. It says the electromotive force is negative the change in time of flux. Thank you. I got to switch to my head. Electromotive force is the unit of this voltage, as we spoke about before. Okay, because it's joules per coulomb. What it means is, if you have a changing magnetic field, i.e., so there's the derivative operator, changes in the magnetic field will induce currents. I.e., if I wave a magnet like this, I will get electrons flowing through a line. Okay, exactly how many electrons is do the math. Okay, you can literally set up a simulation of this and simulate motors. Okay, you can simulate transformers too, which is a little bit more complicated. Okay, I don't have too much more, but I do have a piece of math and some pictures. Okay, so let's do some math. Before we do some math, I want to ask people about if they found any interesting pictures in the books, if they have any comments on what I've said so far. No diagrams. The books have no diagram.
I have a question.
Okay.
Why do they call it Stokes theory and not Stokes law?
It's purely a math thing. It's not really it doesn't really belong to physics. It kind of applies everywhere. And so mathematicians don't like calling things law. They call them theorems.
I see.
Just maybe mathematicians don't like legalese. I'm not sure. Anyway, okay. So we've just slugged through some stuff there. Takeaway really, and I hope I can send these slides up for those who are interested in them. Takeaway is that the units of these are really quite physically meaningful and lucid if you just think about them a little bit. And for most problems, if you decompose the things that are involved into these base quantities, you can get a much better grasp on it. So I have the simplest example of using these that you could possibly have, which is what is the electric field if you literally just have an electron at one point? We'll calculate that fully. Okay, so that's to say, here's my point, nothing exists. I have a negative charge here. What is the force on everything else? Again, it's the simple situation. You can derive whatever you want from Maxwell's equation. You can derive the attraction between two charges. You can derive the magnetic field around complicated magnets, whatever you like. But in our situation, we have one point. There will be some vector field around it.
This is a scenario of like the whole universe is one electron?
Yes. Okay. Yeah. Okay. And so what that means is rho equals 0 everywhere except at 0. So it's just 0 and then some positive, some peak in the middle. I'm going to ignore the details, but you write that with a delta. Okay. Now, given that that's true, okay, you can assume that the resulting electric field will be symmetric, okay, because the equations involving it spherically symmetric. It itself is spherically symmetric. This quotes. I apologize for not going through the entire proof of why that's true. But that means E is a function of just radius. It doesn't care about which point you're at. So the radius of any particular point, how far away it is from our electron at 0, 0, is x squared plus y squared plus c squared. That's the radius squared. Some function of radius squared. And I'm going to give it a different name. Instead of big E, we'll call it little e. And it will be multiplied by the point x, y, z. So this is a single number, different for any particular distance out in space. And this is a triple. What it means is just multiply this by each of these guys. I didn't write it 3 times. And as I write in the subsequent calculations, I'm going to write a single e with no arguments. And so, for instance, if I write this, ex, ey, ez, it means a triple a vector pointed with magnitude in x, e evaluated at this point as x, e evaluated at, okay, know that I'm just getting rid of this parentheses where I'm going. So this is our assumed, it's called an ansatz. This is our assumed form for the electric field. Okay, and now we have to solve this equation. So what we have to do is we take the divergence of this. Okay, so
Excuse me, the little e is the irrational number.
no, I'm not even. We can use a different letter if you really like, but I'm just calling it an arbitrary function.
Okay.
This is what we're solving for. Some function. So okay, so how do you take the divergence of a function? Does anybody remember the formula that I put up a while ago? Let me go back to that. I don't need to go back to it. It's the derivative in x of the x component plus the derivative in y of y component, derivative in z of the z component. So x component is ex. Okay, derivative of a product of functions. Sorry for not going through the full details here. There is a PDF on my computer. I didn't think about timing enough. I did not introduce this rule, but the derivative in x of ex is derivative in x of e times x plus the derivative of x times e. Okay? The derivative of x with respect to x is just 1. Okay, that's the slope of a line. The plot of x is just the vertical line. Slope is always 1. Plus e, and the derivative in with respect to x of e is something more complicated. Okay, so it's whatever the derivative of e is, e prime is usually how we denote it. The first derivative of e, chain rule means you multiply by the derivative of the inside. So whenever you have a composed function, this is e of some other function. So you do the derivative of the outer times the derivative of the inner. Derivative of anything that is not x is a constant. It's 0, so that becomes 0 plus 0, and derivative of x squared is 2. Okay, so we get 2e prime xx plus e. So that's 2x squared e prime plus e. Okay. Again, I apologize for not introducing single variable derivatives and all of this before doing multivariable derivatives, but there's only so much we can do. So that's the derivative of x of ex. It works the same for the other ones. Okay, for y, you get here. For z, you get here. Okay, so that's the divergence of our supposed solution here. Okay, you can does anybody simplify this? Okay, this term that comes out e plus e, 3e, and then 2e prime x squared plus y squared plus z squared. Okay, that is divergence of e. Here you go. Okay, now we get to have fun. We're almost there. Have a wait. Okay, so that is the divergence of e. It has to equal 0 everywhere except for at one point. Okay, so if we set this equal to 0, we can solve this as a differential equation. Okay? So this is thankfully a single variable differential equation. We reduced it so that this is just r squared. I'm going to give it a new name. I'm just going to call it capital R. And remember, when I omit the stuff coming after e, I really mean that it's a function. So this is a differential equation that we're going to solve. Okay, I have it right there. 3e plus 2r equals e prime. We're ready to apply a wonderful trick. Whenever you see a function and its derivative and being added together, logarithms will solve the problem for you. Okay, what I mean is this: we're going to isolate it so that we have e prime divided by e. Okay, is anybody bold enough to come up and solve it so that there's e prime divided by e? There's no calculus. It's just algebra. No? Okay, fine. So divide by e. What's 0 divided by e? 0. 0 equals 3 plus 2 e prime r over e. Okay. Subtract 3. Subtract 3, divide by r, and divide by 2. Now we have our e prime over e. Here's the critical trick. Who remembers the derivative of natural logarithm? What's the natural logarithm? No, the function log. Logarithm.
It's 1 over.
1 over x. Perfect. Yeah. So derivative of log x. 1 over x. We just saw chain rule, which means that if I have a function evaluated of another function, I do derivative of the outer, multiply by derivative of the inner. So what if x was another function? Well, dx of log of f of x equals 1 over f of x. times the derivative of f. It's exactly what we have here. F prime over f, e prime over e. Integral of e prime over e with respect to r is log of r. Okay? In other words, this is a magical, whenever you can rearrange stuff, that you've got your answer. So we do an integral of both sides with respect to r. We know the answer here. That is log of e plus any constant. And then here we do integral of 1 over r, and that is just log of r. Fair enough. The derivative of that is 1 over r. That's minus 3 now. Okay, so finally here, this c we can subtract and bring to the other side. And then we can do e to the power. Okay, so when you do e to the power negative 3/2 log of r, it gets taken out. So this is next slide. That's the integral. That's where we are now. Finally, now we have to solve that. So e to both sides. E to the minus 3/2. Now this time it's actually for consistency's sake. We'll use exp for e to the power of negative 3/2 log of r minus c. I'm going to bring out the minus c. This becomes times any constant c equals e to the log c, e to log e. Does cancel if you just get e. Our answer is that c e to the power minus 3/2 log r. You can simplify logarithms. Log of a product is power. This is exp of log r to the minus 3/2. Okay, and e to the log is just itself. So that's just r. That's r to the negative 3/2. Equals e. And recall that our e is a function of radius. So that means our electric field is literally just that quantity times your position. Okay. So this times x, y, z equals r. And we're done. That's the electric field surrounding point. It points away from the charge with strength 1 over r to the 3/2. Okay, and r was defined as x squared plus y squared plus z squared. You want to think of it as the square root of that is just the distance from the origin. It's the cube of the distance to the origin. So the strength of the electric field, if you have 1 point, is proportional to the cube of how far you are away from that point. Okay, all from Maxwell's equations, all from this. Okay, and of course they can get much more complex. So that's a plot of the electric field in the scenario, or at least the one on slice.
How far you're away from the center, is it?
From wherever the point of the charge.
From the, oh,
Yeah. If you two charges that are very far away, this kind of applies. You bring them together, it gets slightly more wrong because you have to do the real. So you should solve a differential equation with both involved. But as an approximation, this works. Okay. And it's exact if there's only one charge. Yes. Right. So unfortunately, that's the only differential equation we're going to solve tonight. I did not have enough time to prepare as much as I'd like to. We could have done magnetic fields and all this other stuff, wonderful analytic solutions to Maxwell's equation, but you have to settle for that amount of math tonight. I've got some other pictures and not too much else. So you can solve the equation for a permanent magnet. I love Mathematica. I use Mathematica to make that. Okay, magnet, it's just a couple different assumptions. Okay, instead of rho being what it is, you essentially say that there are charges bound up in a magnet. And again, in the beginning part of my talk, to solve any particular situation essentially involves clever choices for what's actually going on with rho, E, and B, and J. Magnet is different assumptions. Okay, you'll see Maxwell's equations with H and another quantity. It's like bound current and bound charge. It's just this other component. You could assume my material does something weird. There will be electric responses in my entire medium that make it different from this, and you have an extra factor. Solve them again with horrible methods, and you get a simulation of the magnetic field. Okay, you can solve it for other shapes of magnets. You get beautiful plots like this. Okay, you can do it in 3D. Okay, here's a solution I did for a bar magnet. Okay, and all of the magnetic field lines going around it. And anything you want. So I've got a couple of applications listed here just for fun, and I'm sorry, but I don't have an actual worked example. Yeah, Mathematica, all three. Yeah,
Hey, if you think that's still around.
I know. Amazing. I don't know why it's popular. I know why it's popular. It's really useful. Anyway, so there's lots of things you can work with, and again, I'm sorry I don't have examples of doing all this stuff, but all of it comes from here and can be worked from here. And it's extraordinarily fun for me to draw this picture and stuff. I think that's the last slide. So there you go. Maxwell's equation. Thank you.
So we have one question online. Are you questions?
Oh yeah.
All right, go ahead. Kay, how have you? If you could
Yeah,
unmute
sure.
yourself.
Thank you. Do these equations ever get, were these equations needed to design or run a magnetic resonance imaging machine?
Yeah, probably. Yeah, definitely. I assume so. I mean,
You
got rotating
do they use them in analyzing the results?
almost surely.
Do we know?
Yeah, so there's a lot of complicated things going to the results, but as the magnets are moving in an MRI machine, your fields are going to be very complicated. And they're designed to, if I understand correctly, to direct a bunch of particles. And those particles might not go in perfect straight lines depending on how you have it set up. So exactly the amount of curve and the angle of curve you expect could probably be calculated. I imagine you could work out my curve is going to be 3 degrees late from where I'm spinning based on this model, based on Maxwell's equation. Yeah.
I'm wondering if you could tell us a little bit the teaser about your
Oh, yeah.
inductance project.
Yeah.
What inductance is.
Yeah. So okay. So thanks for listening to that, guys. But I guess we're trying to pitch our little thing here, which is I want to make a strange transducer. I want to make something that does the following. I want it to emit a magnetic field as an antenna. You can calculate the radiation patterns of antennas simply with models like this. So if I have a circle and it's emitting some antenna pattern, stuff nearby, if there's another loop of wire nearby, it will have currents induced in it, and that will be a draw on your emitter. So what I want to do is I want to calculate the position and shape of what is drawing the load on my antenna, purely based with only information I get from my emitter. Okay, so this is done. This is done with cars. They have loops of wire in the road that emit waves. Your car picks them up. Eddy currents are induced in your car, and based on how many eddy currents are, how much load it's putting on this source, it can deduce if you're a truck or the size of your vehicle. It gets more induced currents is a bigger vehicle. But I think you can get precise with it. So I want to do exact numerical solutions of what shape is picking up, is receiving my antenna. What exact shape is receiving based on, again, only information from my emitter. I think it's possible. Okay, so
you will look at the shape of the second antenna.
yes,
Based on the emissions universe.
yes, calculate the shape of the second. Thank you
Not just
for
the mass, not just the total volume, but the actual shape.
yeah. So I think I can do the other method quite straightforwardly in Mathematica and say if it's a square and a circle and they're this offset by this, here is the coupling coefficient between. Here's the formula for the coupling coefficient. So it's essentially it's just a double integral over each. Here's loop 1 A and here's loop 2 B. And if I just do 2 integrals around them for every point on each, for every pair of points between each, how far away they are and where they point to each other. That's how much. So that'll be some number. You can normalize it, but some number between 0 and 1. for how much it will pick up. So I can calculate how much should it draw if it's a square or and a circle, and how much should it draw if it's a different shape in a circle. And for any pair of shapes and positions, I can calculate how much do I expect it to be parasitically a draw from my source. And again, it's just the inverse problem. So instead of knowing A and B and calculating that for any particular shape, B is undetermined, and the frequencies that are being fed through this shape A is known. Calculate B. So it's a horrible inverse problem. I think it's possible to do. So I want to put together a little antenna and a little receiver and actually calculate the shape of the receiver if we bend it.
You have two different shapes which both have the same spots.
Yeah.
That's good.
Unfortunately, yes. Similar problem is hearing the shape of a drum. You can calculate the pitch that will come off of a drum, what frequency it is, and what exact distribution of sounds it will produce, just based on its shape. You can model the sound a drum should make, but can you hear the shape of a drum? If you hear a particular tone coming off of this, can you calculate what shape it came from? And the answer is no, but kind of yes. You can't do it modulo the area. You don't know the area of the drum, but you can, but if you assume it's a convex polygon, you can. So this is just a similar horrible inverse problem, which sort of has an answer.
So this is an open problem. We have not solved this, but if you want to be a part of the team that is solving it, come talk to me because we'll be starting that early in 2026.
Does your antenna illustration, is that affected by the distance between the emitter and the receiver?
Yeah, so far field, the answer is going to be 1 over r to the -3.
Yeah, it's simplified.
Right.
Zero.
If the point is small enough, limit as the point goes to 0, they'll just get that. So farther away is less. But like, there's a lot of practical considerations that we're going to have to do. I'm a little frustrated by it. I don't want to think about practical considerations. Namely, like, if I'm feeding anyway, if I'm feeding a voltage through the thing, and my receiver is nowhere to be found, I'm going to just burn it because I've got no load whatsoever. I don't just want a closed circuit. So it's going to have to be adaptive and do some. I don't want to think about this, but I have to. So
We have another. Go ahead.
Sorry, how is the equation here affected by a transmitter and 2 receivers? Could you just simplify it in terms of view the 2 receivers as being a single receiver?
You have to do a triplet integral.
Okay.
So in general, so I showed you guys before an application of Stokes' theorem. This is the result of Stokes' theorem. Okay, the real solution that is not pathologically take into account every antenna nearby is just a surface integral. So you do a volume integral. This is just a converted form, so you can calculate with loop integrals.
Yeah.
And
We have a question online, Prismic, if you want to unmute yourself.
Yeah, so I think the reason why those convolutions are difficult to reverse is that they kind of, they integrate over the whole area, right? And so the standard trick used by MRI and CAT is that you do the measurement from multiple configurations, multiple angles, multiple positions, and so on, right? And then there's a unique solution that's sort of like if you have integral from this direction and this direction and this direction and this direction, you essentially can solve it, right? So is that something that you could do for your inductance problem?
So one thing is two degrees of freedom that we gain. So not one is by feeding many combinations of frequencies and in general non-periodic waves out to the antenna, and keeping specific track over when you hear the reflections back according, if you had the ability to send a pulse at any time and measure the pulse coming back, you get a lot more information. And then if you could space the pulses in any way you like. I think that gives you more degrees of freedom. I won't say more, but the second way to get more degrees of freedom is, of course, just to have multiple emitters that are doing in tandem and doing different combinations of signals in tandem. So like a hyper advanced form of triangulation, because if you're just assuming each emitter gives you a distance, and you can work out where those circles intersect. But again, I think you can get shape information. Beam forming sort of stuff, or using beam formers as a transducer.
Can these equations be applied, say, to the surface of water in a swimming pool?
If you think of water as electrically conducting medium, then yeah.
Yeah, it's a way.
Yeah, but the wave equations for water are analogous, but not the same. I believe they're missing a negative. There's only one field, and you don't have a split where you get E and B. There's more you can look into after this talk. There's a version of Maxwell's equations which involves a single quantity that I spoke about at the beginning. And if you want to talk about analogies to water and gravity and anything else, Maxwell's equations can be written like amazingly. You just use these other quantities. So this is literally Maxwell's equations if you use the vector potential A. E and B can be written as formulas in terms of A, the vector potential. And Maxwell's equations literally reduce to the following, assuming those definitions. Square of A equals 0. That's it, done. Okay. Square is D'Alembert operator, which is the second derivative in position, summed minus the derivative of time. But easy to define. Find it as this, because that's the D'Alembert. And I think if you want to draw an analogy between other fields of physics, you can literally just tweak the definitions. So if you look at what is B in terms of something of A and what is E in terms of something of A, you just see that water is this, but change in negative. And the universal equation is D'Alembert. Okay. It gets even wilder if we look Lagrangians and stuff like that. Because you just do an integral of this basically and derive a rule of all of physics. It gets really beautiful, but I don't know that. Okay, it's horribly abstract. This is the level of abstraction I'm. So thank you guys for listening, and I'm curious about the math club, and I'm curious about the ham radio club. I actually would like you guys to tell me a little bit about when you guys meet and what you guys do.